So in the last video, we talked about the notion of span. And in the chapter before this, we talked about the idea of representation of zero. And in particular, when we're talking about sums, we talked about unique representation. Linear independence builds on both of these themes. So let's start, as we always do, with the definition. So for the setup, we say a list of vectors v1 through vn in vector space V is called linearly independent when any sum aivi equals 0 implies that all the ai are 0. Oh, and also the empty set is linearly independent vacuously. So what does this have to do with the unique representation that we were talking about before? Let's consider the situation where you have some vectors, and then we have a vector W inside the span of some V's. What this means is that W can be written as some sum of the VI's. But now we can ask ourselves, what if it was not unique? What if there was some other way of representing them as well as AIVI's and then also as maybe some BIVI's? Well, then I could subtract these things and I could write 0 equals the sum of AI minus BI times VI. And so if this set is linearly independent, then this forces AI minus BI to be 0. So we would say linear independence implies that all of those coefficients are 0 because this is a sum of some VI's. All the coefficients are 0. And that in turn means AI equals BI. So in other words, linear independence can be rephrased all elements in the span can be written exactly one way. And I think that's ultimately the thing that makes this property so useful. So let's take a look now and see if we can do some calculations, sort of practice this. So we talked last time about the Euclidean spaces and how they have simple spanning sets like 1, 0, 0, and so on. These are clearly linearly independent. And the reason is because each thing has a 1 in exactly one slot. So each element of this list controls exactly one entry. And so if you ever have a 0 in any particular entry, it means that that vector is contributing nothing. Well, the 0 vector, zeros everywhere, that's just got to be all zeros. So it's sort of on the nose. We could say something similar with polynomials. So we also talked about the space, the vector space of polynomials, or however you want to write it. And we can see that, for example, 1x, x squared, up to some amount is also linearly independent. Although, unlike the previous example, that's not even English anymore. Unlike the previous example where this is linearly independent and also it's spanning, right? Everything is some combination of these. Independent. This one's not spanning. Let's see if we can come up with an example slightly more involved. Here's my favorite example. Let's look at the vectors 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's call these V1 through V3 inside R3. This is an example that's actually not linearly independent. And the way that we check this is also Gauss-Jordan, funnily enough. Because remember that what we're trying to do when we're looking at linear independence is we are looking at a system of equations, namely the system of equations you get by looking at each entry of this vector and each coefficient and setting that equal to 0. So in other words, for these things to be linearly independent, I should analyze the system of equation a1v1 plus a2v2 plus a3v3 equals 0. And we saw what that looks like. It gets me a system of equations that looks like this. And let's see if what we find about the relationship between the A's. If I Gauss-Jordan this, we'll start with the first row, and I get 0, and then I have to subtract 8, so I get minus 3. And I subtract 14, so I get minus 6. And then I subtract 3 copies, so I'm subtracting 12, and I get minus 6. 7 times 3 is 21, minus 12. And now we can do some simplifying, right? I'm going to squeeze it in a little bit because I can see that these can simplify. And now when we keep going, we get 0, 1, 2. This becomes a row of zeros by subtracting row 2 from row 3. And then here I get 1, 0, minus 1, 0. So what do these equations tell us in practice? They tell us that A1 minus A3 equals 0. A2 plus 2A3 equals 0. And that last equation is now not inconsistent. Previously, we saw 0 equals not 0. This is fine. It's just that this equation disappeared. So it's not helpful. And so it's kind of like I'm only dealing with 2 equations and 3 variables. So what that means is one of these variables is underdetermined. And so the upshot then is the best that I can do is give you a formula for these things in terms of other things. So typically what we tell students to do is take the variable without the leading one, that's this guy, right, A3. Treat A3 as a parameter. In other words, we give the answer of each of them in terms of A3. So we would say A1 equals A3, and A2 divided by 2, or sorry, A2 equals 2A3. That seems like it's easier, right? It's just a simple formula. And so this tells me if I know A3, then I can give you a linear combination. And in particular, since any choice of A3 works, there must be infinitely many ways of doing this. Infinitely many solutions to this system. So what we're seeing is infinitely many solutions to the system is the same thing as linear, not independence, but dependence. Linear dependence is just the opposite of independence. It means that, it's not the case that this is forced to be 0, or in other words, there is a non-trivial relationship between the vectors. So linearly independent means that there's no relationship between them. Linear dependence means that some of them are combinations of the others. Okay, what time is it? we've been going for 10 minutes. That's plenty of time. We can keep going. Next up, let's do a little lemma. This is lemma 2.19 in Axler. He just calls this the linear dependence lemma. And here's the statement. He says, suppose that we have a list of vectors in V and they are linearly dependent. Then there is a VK in the list, right, among them, such that VK can be written as in the span of all the others. The way that we denote this is we put a little hat on. Oh, sorry, that's actually not the statement of the lemma in Axler. A stronger statement is in the span of VK minus 1. Okay. So where was my confusion? I was thinking that the lemma says if there's a linear dependence, then one of the things is redundant. That's true, but it's not exactly what he's saying. He's saying something slightly more. Axler's telling us that what I should do is I should start with V1. A single vector is always linearly independent, right? Because of course it is. Then we look at the list of V1 and V2. And we see, is that linearly independent? And if yes, we keep going. And at some point, we will encounter a situation where VK was not linearly independent, but VK minus 1 was. Right? When we add in some new vector, then the conclusion, right, is that the span up until VK is equal to the span up until VK minus 1. In other words, you could throw away that extra vector that you found as you worked through it. So what I've said here is somewhat close to a proof. The only thing that I really need to do to prove this is, I mean, this is sort of the beginning of the proof, right? As we find this critical vector because we're assuming that there's a linear dependence somewhere, which means it must transition from independent to dependent somewhere. And we're calling K the point at which it depends. So therefore, the only thing I have to do is I need to prove this equality for us to be done. And one direction of this is completely trivial because, of course, it's always true that a list of fewer vectors will be contained inside the span of a list of bigger vectors because all of these guys are also in there. So if you could write something as a combination of these, you write it with the same combination of these, you just ignore VK. So that's trivial. For the part that's genuinely new, what you should note, for the reverse direction, in other words, that the reverse inclusion holds, what you should notice is that since V1 through VK minus 1 are linearly independent, then what I do is I take my sum AIVI, where I ranges up to K, right? Since that's equal to 0, the thing that we're looking at, I can break off the last thing VK, right? I could write this out as A1V1 plus AK minus 1 VK minus 1 plus AK VK. And then let's put this guy over here and divide by AK while we're at it. And then I get VK equals minus 1 over AK, A1V1 up to K minus 1, VK minus 1. And the conclusion then, of course, that we could distribute this if we were so inclined. But what that does is it proves that VK is in the span of these other vectors, right? This is a linear combination. And so that gives the non-trivial direction of this inclusion. And therefore, I could remove VK from this without affecting the overall span. Okay. How long has it been? Should we stop here? It's been 15 minutes. We should probably stop here. There are one or two more little facts that I need to tell you in this section. And so we have one more thing we have to do, I guess, but that's okay. We'll pause here for a moment, give ourselves a little bit of breathing room, and I'll see you guys in just a few minutes for those last couple of facts.